To this classic paper by Raup and Gould, which was the first in a series of important papers on quantitative paleobiology in looking at the dynamics of the fossil record, which included the very famous work on punctuated equilibrium. But this was the first one, towards a nomothetic systematics. And the word nomothetic refers to the development or the articulation of generalized laws in science. And it's something that obviously we all secretly strive toward, and I'm just going to be explicit about. That is the goal here, about trying to understand the underlying structures in taxonomy and whether we can articulate those in a way that's useful to measuring biodiversity in the past and the present. So this is the long drawn-out version of background to let people wander in through. So it's also important that we're all on the same page about what we mean by systematics and taxonomy and phylogenetics. So phylogenetics and systematics are not the same thing. A lot of us who are evolutionary biologists work on both, and we see a lot of overlap between these different topics. But systematics, the classification of organisms, is not necessarily dependent on phylogeny. As evolutionary biologists and in this modern era, we feel that that is the best way, the ideal way to articulate relationships among organisms, but it's not the only way. But anyway, we're just going to assume it is the best way. It is the goal of phylogenetic systematics to classify species according to evolutionary patterns. And so one of the big abiding questions in systematics and phylogenetics is whether there is a fundamental disconnect between morphological systematics, as we use in paleontology, and rank-based systems like the Linnaean classification. So this is important as well because the genus and the species, even if we ignore all other higher ranks, which become very, very contentious, genus and species names, the binomial epithet, goes along with effectively all organisms. So we can't escape, especially the genus unit, as a collection of species. And there's a phenomenon which could be called taxonomic surrogacy, which is so common that it gets ignored. And this is the substitution of higher ranks when you can't identify something to species. So this is very familiar to paleontologists. This very famous extinction curve on the left-hand side of the slide is something that we take completely for granted, but it's a measurement of biodiversity through time, but it's specifically a measurement of, hi, that's my co-author. Look at him. Look at him and shame him. So taxonomic surrogacy is when we take higher ranked taxa and we use those as a substitute for measuring biodiversity. So instead of counting species, we count genera, or we count families. And everybody does this, not just paleontologists. So we are not alone as paleontologists in doing this. It's also extremely common in environmental impact studies in neontology. So if you go out to the field and you just want an assessment for some reason of how much biodiversity is in a space, you can't necessarily identify everything. Maybe you need molecular identifications, or maybe you're just not an expert in particular groups, okay? But the problem is that, as we know as taxonomists, genera are not equal units. Genera and higher ranked taxa are not equal units. So a genus can contain one species, or a genus can contain 1,000 species. So if we know that there's this level of variability in the units, what does it mean quantitatively when we start to use those larger units as the basis for our counting system, as the basis for our currency? So that is the question that this study basically addresses. Okay, so genera are not all the same. Genera are not equivalent units, but is there some underlying pattern in the way that they're distributed and the size, the species richness of genera? And in fact, there is, and actually, it's relatively well known. So this has been discovered and rediscovered repeatedly in the literature, which is kind of interesting. And also several of the papers that have been written on this topic point out that this has been discovered and rediscovered repeatedly, and taxonomists are forever finding this out and thinking they've discovered something new. And it follows the same kind of distribution that's familiar from economics. So a skew distribution. Not all natural systems produce normal distributions. It's sort of more intuitive to us that we always think that the goal should be a bell curve, but the other very common kind of natural distribution is a skew distribution. So a Pareto distribution is very familiar, very common, especially in economics. Pareto distribution is the probability distribution that explains the size of corporations or the distribution of wealth. So there are a very large number of very small mom and pop shops, and there's a very small number of mega giants like Amazon and Microsoft. And likewise with genus size. Okay? So there are a very, very large number of monotypic genera, or genera with very few species, and the number of genera with very large numbers of species are comparatively rare. But what's quite interesting is that the distribution of this, the proportion, the way that the species are distributed into different genus units, is actually completely consistent across all different metazoans. So when you have a sufficiently large sample size, about 30% of any clade or any large group of organisms, about 30% of species, 30% of genera are monotypic. Okay? So this is really interesting, and this is new data that we gathered as part of this project. But these different clades follow very different taxonomic conventions. The rules that you use when you're naming a new species of lizard are very different than the rules that you use for naming a new species of chitin. So it's quite interesting that despite these partitioned, independent taxonomic approaches, in different groups of metazoans, you still end up with the same, very, very similar distribution. So previous papers, I told you there's already quite a lot of literature about this, and a lot of it's been dismissed as the skew distribution is somehow wrong. Okay? That the numbers of monotypic genera especially are perceived by taxonomists as being problematic, that they represent an overabundance of splitting or a tendency to seek out novelties or to highlight and identify novelty in a disproportionate way. So the fundamental question again is whether real-world taxonomy, or what the established taxonomy is compatible with a true all-knowing phylogenetic systematics. So in this project we said, well, we can just test that. We can play God. So if we have synthetic taxonomy on simulated trees, then we know the tree, we know the phylogeny, it's in silica, and we can just apply the absolutely perfect rules of taxonomy that we invent and determine what the distribution of size, species richness among the different ranks is. Okay? So this comes from simple birth-death models, very, very simple trees. So I want to explain to you, because this also has many applications in other areas of phylogenetics, and I think it's important to understand a little bit of the maths of how these birth-death models behave. Okay? So in a birth-death model, to make these synthetic trees, you have three options. So you start with a single ancestor taxon, and then in the next generation, it can either split, and there are two daughter taxa with a certain probability, or it can go extinct, and then game over, or it can just carry on, not split, not go extinct, just carry on with a single species. Okay, that's it. So there's only two parameters in play. There's a probability of speciation, and there's a probability of extinction. So these parameters, it turns out, have a very simple maths, and that determines all other behaviors of the clade. So the gray shaded angles on this diagram represent the probability of total extinction. So if you are, if the set probability of extinction is greater than the probability of speciation, then you might get lucky for a couple of generations, but eventually everything goes black. Okay? But in different areas, does this work? Yes. Okay, but in different areas of this part of the diagram, where you have a certain probability of lineage speciation, which is down here on the bottom, which is greater than the probability of extinction, you have an increasingly good chance of your descendants carrying on. Okay. So we can sample across that space. So in our simulations, we chose parameters to deliberately sample across that total extinction probability. The other thing that's most important about these simulated trees is how big it gets. And this was actually what Raup and Gould studied extensively, and what they were most interested in was this balance between explosion, massive radiations, versus totally crashing out. Okay? But it turns out that that is just controlled by the difference, literally one minus the other, speciation, extinction minus speciation. So all of these dots on my diagram are chosen so they have the same difference, so they produce, on average, the same size of tree. Okay? And interestingly, if you go off this little line that we've chosen, it rapidly turns into these crazy explosive speciations. So you just have to move a couple of steps down, and suddenly you're into a single tree producing 10 to the 17 descendants, which is living descendants in the end game, which is obviously just not biologically realistic. Okay, so we made lots of trees, tens of thousands of trees for each of these different parameter sets, and then we imposed different taxonomic rules on these trees to look at how they compare to empirically determined real-world taxonomic distributions, species richness distributions. So I'll briefly walk you through the two different taxonomies. They're not particularly important. It's more the patterns of the results that are relevant. But the first one was a relativistic approach, so a proper phylogenetic systematics. So basically taking any sister pair and calling them a genus, and things that are more closely related to each other than they are to anything outside the clade are a genus, and otherwise they split. Okay? So to remind you of our empirical data, here are the real-world taxonomy. Look at them, they're all incredibly the same. We also have data for reptiles and fish and a couple of other groups which are left off this diagram simply because it becomes just too many colors doing exactly the same thing. But let's stick with the marine invertebrates. So this is a sampling of about 30,000 genera, not species, genera. So that's sort of our comparator to the simulation data. So from that first algorithm, this is what you get from simulation. So what's interesting is that it's also very, very tightly constrained. There's this funny artifact because in that particular algorithm, all pairs are defined as being a genus, so we suddenly end up with an unrealistic or an unusual number of genera that have 2. Okay, but that's all right. So as an alternative, what if you just use a fixed distance? So a chronologically defined genus that's cut off at a particular depth. And so this actually is interesting because it turns out to be a much more broadly dispersed spread of distributions, even than what we got from the real-world data. And that's a key point. So there's very strong similarities between the real taxonomy, which is very, very highly constrained, and the simulated taxonomy. So that's good news. It means that phylogenetic systematics is not, perhaps, a process which is doomed to defeat. But interestingly, another key point is that large genera are very rarely encountered in the simulations. They're much more common in understudied groups. So in the marine invertebrates, you get outrageously large genera of thousands of species, but they never ever get spat out by the simulations. And interestingly, the real taxonomy across all these different groups of metazoans is actually much more constrained than what you would get from, say, a chronologically defined genus imposed on omniscient trees. So genus size frequency it follows a skew distribution that arises apparently from the natural properties of trees. Even though all of these, not all, but the vast majority of genera that are involved in the empirical data that I'm showing you are based on morphology, they're not everything has been updated with a phylogeny, they still seem to correspond to the maths that we find from trees in simulation. So the established taxonomy is not necessarily in conflict with phylogeny, which is good, and it also means that there are patterns in here that we can find, understand, and eventually apply to understanding biodiversity in the fossil record. And then to the point about large genera, the simulations also imply that large genera are probably unrealistic in the majority of circumstances, or they should be very rare. And so if there was ever a war between lumpers and splitters, the point goes to the splitters. Thank you.